To begin this rotational motion experiment, we'll need to determine the mass of the weight hanger. Then we'll measure the diameter of the largest pulley on the rotational sensor using our vernier caliper. For the most precise results, make sure that the jaws of the caliper are measuring the internal diameter of the pulley. Next, we'll activate our GLX and navigate to the graphing screen. Here, we want to make sure that the GLX will be displaying a plot of angular velocity versus time. Placing a small amount of mass on the weight hanger, we'll now wrap the string around the same lower pulley, winding up the length of the string until the weight hanger is just below the black pulley. Before we release the weight hanger, we need to make sure that this other pulley is aligned such that the string will smoothly transfer from one pulley to the other. Then we will press the play button on the GLX to begin data collection, and quickly release the assembly. Once the length of string unwinds, be sure to stop data collection by hitting the play button again. The GLX should display a very linear-looking plot of angular velocity versus time. To determine the slope of this plot, we will move the GLX cursor along the linear portion of the graph line and obtain two sets of coordinates. The slope of the line will represent angular acceleration, denoted by the Greek letter alpha. A number of calculations will then need to be performed. These include determining the acceleration of the falling weight hanger, the tension in the string, and ultimately the moment of inertia of the entire system, including the silver disc. We'll then add some additional amount of mass to the weight hanger and perform another drop test. And once the relevant data is collected for this test, some additional mass will be added and one more drop test will be performed. With 3 data sets completed for the assembly with the silver disc, next we'll add this hollow black cylinder to the top of the silver disc. Ultimately, it is this black cylinder that we are trying to determine the moment of inertia for. But in order to determine an experimental moment of inertia for the cylinder, a combined moment of inertia for the cylinder and disc must be ascertained. To safely combine these two elements, notice that the cylinder has a couple of special tabs that will secure it to the top of the silver disc. And because the disc adds a substantial mass to the rotational assembly, we'll need to add more initial mass to the weight hanger than we used in the first set of trials. However, once this mass has been added, we will wind up the string on the same pulley and perform 3 drops, just as we did before, in the last 3 trials without the added black cylinder. For each subsequent trial, the mass on the weight hanger will also be increased as before. Once the pertinent calculations for these drops are performed, a very interesting additional value may be determined. In the first set of trials, we determined the moment of inertia for the silver disc and all of the hardware inside of the rotational motion sensor. On the surface, this may not appear to be of much use, but remember that in the second set of trials, we figured out the combined moment of inertia for the hollow black cylinder, silver disc, and rotational sensor hardware. So now, we can take the combined moment of inertia for the hollow cylinder, including the silver disc, and subtract from this the moment of inertia determined for the silver disc and other hardware in the rotational motion sensor. Notably, because the moment of inertia is simply a combination of the mass and the geometric distribution of this mass from an axis of rotation, the moment of inertia can simply be geometrically summed. This allows us to determine a moment of inertia value for just the hollow black cylinder. In the second procedure, we will compare our experimentally determined moment of inertia to what we would theoretically expect by using a textbook formula for determining the moment of inertia of a hollow cylinder. To utilize this equation, we will first need to determine the mass of the hollow black cylinder. We will use the vernier caliper to measure the external diameter, as well as the internal diameter of the cylinder. Notice that these other jaws for the vernier caliper are very convenient for measuring the internal diameter of the ring. Using the standard equation for the moment of inertia of a hollow cylinder, we can then determine the theoretic moment of inertia for our black cylinder.